Welcome, Kit, to Func Prog Sweden, straight from the Pine
Hello.
Woods.
Yes, exactly. This is really where I
Welcome.
am.
Yeah. Welcome to Func Prog
How's it?
Sweden. The stage is yours.
It's good to be here. Thank you so much.
You're welcome.
Very excited. A little nervous. I'm exploding with butterflies. This is wonderful. And they belong in a forest setting. Okay, I'm gonna share my entire screen. Let me just make sure I have a nice peaceful space here. Okay. Ooh. Ta-da! I snuck ahead. Okay. Hello, everybody. So yeah, I'm going to talk to you all about algebraic effects. And if you don't know what that is, great. And if you do know what that is, cool also. Hopefully, by breaking it down into a nice choking hazard size pieces for babies, we can all sort of get it into our heads one Lego at a time. And yeah, so there's going to be some rambling. That was a little taste of rambling at the end. So usually when you give a talk or any sort of performance, you want to have a really strong opening and a really strong end. And the middle almost doesn't even matter. There's some rule for this. I've sort of flipped that chart around. The x-axis reflected it. So there's going to be a lot of rambling at the beginning, a bit of rambling at the end, but I think the middle is pretty solid. So stick with me, and yeah, we'll see if that works. Maybe that'll turn into a presentation strategy. It's mine of choice. So yeah, algebraic effects for babies. So let's go over the agenda for today. Step one will be to define myself. Who am I? Why am I talking? Why should you care or listen to me at all? And I'm not sure if that's going to be very compelling, but we'll see. Secondly, define algebraic effects. Just a little really tight animated synopsis of what we're going to dive into. And then we're going to look at some examples, particularly using this one new fancy algebraic effect library for Scala called Kio, which I sort of started perusing recently, the open source code base of, and learned a lot. And that prompted me to give this very talk. And then we're going to implement it from scratch, the name of the talk, or the previous name of the talk. So let's begin. Hi, I'm Kit, and I dropped out of art school, I don't know, a decade ago or 8 years ago or something like that, because I was spending all my time learning to program. I got really obsessed with that. So I said, that's probably a better order of operations, is to have a job that actually had some kind of compensation. That'd be cool. And so I joined a boot camp where I learned Ruby on Rails and JavaScript and all this. While there, they hired me actually. And then I did a bunch of teaching and used a whole bunch of other languages, just kept getting obsessed with programming languages. So I learned Elixir. That was my first functional programming language, sort of. I did pattern matching, which seemed very magical, felt like a magic trick. And then from there, I learned Elm, which had the mystery of white space function application. It has a Haskell light syntax. And so that seemed to just violate the laws of syntactic physics in a way. It was very perplexing. Obviously now in hindsight, that's stupid. It's just syntax. But at the time, oh my God, it blew my mind. I thought you needed parentheses for some reason to cup the arguments so they just all fall apart. Then I finally, beckoned by the shibboleths of Haskell and Monad and Functor and applicative. I was like, what are these crazy riddles? I want to learn them and be anointed. And then after doing that for a few years, I was like, I actually want a job. So I found Scala, which is like Haskell minus type inference plus job opportunities, I guess. And I kind of was a begrudging Scala user for a year until I found this library called Zio, which is this functional effect system for Scala, which I liked a whole bunch. And it felt like the apex of everything I liked, from the sort of usability of Ruby on Rails. Ruby in Rails? What have I done? Ruby in Rails, sure. But also sort of still having this very powerful type system. And it brought back a lot of type inference that I was finding lacking in the other Scala FP ecosystem. I don't like manually typing things. And so I started doing open source for them, did a whole bunch of macro things around dependency injection and stuff, dark magic. It was a good time. And then most recently, Flavio Brazil released this new algebraic effect library for Scala called Kio. I read the code base. I wanted to understand how it worked, so I implemented a toy version for myself. had a lively, fun, engaging discussion with Flavio on GitHub, and we actually it led to some changes in the design, which is super cool. So I'm glad that that kind of means that I understood it, hopefully. Yeah, and I thought that was it's such a fun and beautiful and elegant design that I thought it would be cool to kind of break it down and walk everyone through it. So that's the plan for today. That's the me slide. Algebraic effects, let's define them at a very high level. And just bear with me. Sometimes we're going to, I don't know, I might use some words you don't understand. Feel free to interrupt or ask Magnus to interrupt me, and I'll try to give you some bespoke rambling just to your point, and just sort of Tommy gun that with metaphors until it breaks apart or you tire out, whichever comes first. So algebraic effects. Algebraic effects are an extensible and composable functional effect system with a distinct focus on severing syntax from semantics. It's a bit of a mouthful, and we'll break that apart. You could also say it's separating syntax from semantics or decoupling syntax and semantics. And basically, it's this user extensible version of a functional effect system. It's very neat and modular and not just this giant behemoth as many of them tend to be, and also very powerful at the same time. And it has an elegant core that can be possibly explained in the length of a single conference talk. We will see if that's true. Functional effect systems, I'm not going to go into too much detail here because Func Prog Sweden, I think we know a little bit about these, but once again, if you want me to go into any more detail, I can answer additional questions at the end. To sum it up, I feel like the best three-word explanation is they're programs as values. And this comes from a great blog post by Fabio Labella, who works on the Unison programming language now and was a big Scala contributor before, and maybe still today. The idea being that you write your programs not as side-effecting things, but as these sort of workflows or blueprints that you combine together, building larger blueprints, and then you execute them at the end. And this gives you a lot of nice methods and powers and reasoning capabilities. You get some very beautiful ways of dealing with asynchronicity and concurrency. And you can just do a whole bunch of things really trivially that take a whole bunch of work and headaches in imperative style. So this is a declarative over imperative style. And to steal from another person whose work online I like, Runar Bjarnason, who wrote Functional Programming in Scala, he gave a talk a while ago comparing the declarative program as value style to being sort of dynamite, this abstraction of an explosion that is easy to manipulate. You know, you could just give it to your kids, they could juggle it. And then if you want to blow up a building, you can neatly place the dynamite around the building and then safely blow it up from afar, versus the imperative analogy would be you sort of light yourself on fire, you're on fire, your kids are on fire, you all run into the building's on fire, and then hopefully, you know, you get paid. I don't know. It's less nice. Okie dokie. So that's functional effect systems. Syntax and semantics, a brief, I don't know, few metaphors to just whet the palate before we dive into the thing that is really going to build from first principles. So this might lose you for a minute. Once again, we're sort of reaching that apex of organization and hopefully understandability of my talk. Still powering up. The butterflies are slowly dying, and I'm gaining composure. We'll see. Syntax and semantics. So syntax is guided yet meaningless structural patterns. So it's a sort of set of rules for building structures. You know, the grammar of a written language or the syntax of a programming language. It doesn't actually have any meaning until semantics is bestowed upon it by interpretation or compilation or transpilation. And the syntax is just some structure, but semantics is the interpretation of that structure. Syntax introduces structure, semantics sort of eliminates that structure, leaving a resulting smoldering value at the end. So syntax unfolds something, semantics folds that structure. So you unfold into a structure and you fold it back down. Just some fun functional programming words to throw out there for the bingo cards. Okay, and then two other thoughts that I thought were vaguely interesting. Programming languages like to give you hooks into, they give you ways of maybe building your own syntax and semantics. And we might not think of this as being generating our own syntax, generating our own semantics, but in a sense, that's kind of what method definitions are. Every time you define a method, say like this here, add method, you're kind of defining your own bespoke syntax. So add 22.5, this is kind of meaningless until we, what do we do? Until we interpret it. So we need a method body, and a method body is going to provide semantics. So we could define this, sort of the logical way, which will be A plus B. Or if we felt like it, we could do A minus B. Who cares, right? Semantics and syntax are disjoint. We could also just return a very large number. Now, hopefully you implement this in a logical way, but they're sort of separate. And method signatures allow us to define a syntax and a semantics. It's something we do every day. We're always dealing with syntax and semantics. A slightly more subtle, weirder version of this is to consider data structures. And you can kind of consider any data structure, especially algebraic data types and data structures, as syntax. So when we're building, say, this list here, concatenating a bunch of singleton lists together, you can kind of think of this as creating a syntax tree. And then when we call these list methods which fold over the list data structure, these are sort of providing semantics in an ad hoc manner to the syntax tree. So list.max will sort of reinterpret this meaningless syntactic plus plus operator as the max method, getting the maximum of 2 ints. Sum is reinterpreting plus plus as, well, just the normal int addition, and product would reinterpret plus plus as multiplication. So data types are sort of merely just syntax trees. Every single one of them is a syntax tree. It's a suspended computation, the suspended idea, not even a computation, suspended structure, which is going to be semanticized. No, that's not a word. It's going to be lended semantics to by process of folding later on in the program. If you don't eventually interpret a data structure, uninterpreted data, if a tree falls in the forest, if a linked list is constructed in the forest and no one is there to interpret it, is it useless? No. Yes, it is useless, rather. Is it useful? It's not useful. Okay. And to really get rarefied just for a moment, just for fun, before returning to Earth, so please hold on, suspend your disbelief if this is totally nonsense to you. Let's take a trait like monoid, if you know what monoid is, which is this type class, this bundle of methods which for a type A provides an empty method and then a combine method. So we can get this pull some empty value out of thin air and then also combine 2 values. We could then create a syntax tree for this trait. Just imagine like we're writing a syntax tree literally for the structure of methods. Empty could be represented by this empty case. Combine could be this combine node, so it's just a syntax tree. We're also going to add one special little sidecar case so that any value can participate, while supplies last in this enumeration. And then if we mush it around slightly, we actually get the list. So empty is nil, and the cons case of a list is a sort of smushing together of the value becomes the head and the combine becomes the tail, this recursive tail node. So it's just a more compressed version of the syntax tree of a monoid, and that's why the list is known as the free monoid. The point is, the list is really just a syntax tree for a trait, and therefore we interpret it later by folding over lists. So if we take an instance of our monoid, perhaps the addition monoid, defining empty as 0 and combine as int addition, that is isomorphic in a sense to folding over a list of ints and providing 0 as the empty value and then addition as the combination operation. And so 0, 0, a plus b, we're kind of just providing an ad hoc monoid instance. Those are the arguments to fold. They're just sort of basically providing semantics for the data structure. So you could define folds for really any data type. And then that is, the arguments to fold are basically just the semantics of the structure of the data type, which is cool, or perhaps completely inscrutable if you don't know what I'm talking about. So that was a fun ramble, just to set the scene, some metaphors to whet your palate. Let's look at some code. And then we're going to return to this slideshow for more fancily animated from scratch animations. But first, algebraic effects, I want to give you an actual anchoring idea. And so we're going to look at Kio, and I'll make this real big. Let me know if it's ever too small. So Kio is this new library for Scala, which is very, very fancy and well designed. And it's still, I think, relatively early in its development, but so, participate on GitHub, take a look at it. Flavio is a really great developer and a very friendly fellow, and nice to collaborate with. So definitely check that out if you're all interested. Okay, so what do we have here? So it's a for comprehension, which we're going to look at in more detail later. Just a way of sequentially composing logic inside of a functional effect system in Scala. And we have this thing that says consoles.println hello Func Prog Sweden, a little pandering. And then I'm going to click run on this little object here, and we will see hello Func Prog Sweden printed to the console. So I could, if I wanted to, duplicate this line and say goodbye Func Prog Sweden and make it red and run this again. And we'll see that one is executed after the other. And so we're building here an algebraic effect, and it has a certain type signature, which we're going to look at here. This effect returns a unit, which is this type down here. If I said yield 10, this would instead return an int, if we felt like returning 10. And it depends on this consoles effect. So before we can actually get this final int value, we have to deal with consoles. And it turns out that this is sort of built into this Kio thing. So by calling run, it will handle and execute this consoles effect. So that will work. But we have more effects than just consoles effects. We have these modular effects that we can combine together and run one at a time in different orders. So one interesting effect that we can look to is this environment effect. So if I want to, I could grab a number, a magic number out of thin air. I could say ends int.get, and this is going to change the type signature actually. Now I'm going to actually just return this number times 1000. So what we have here is now an int that depends not only on the consoles effect, but also an environment of int. And what this means is it's sort of analogous to turning it into a function that now takes an int to run the body. So later on, we're going to have to provide an int, and that's what's going to get popped out here. At least that's one potential semantics given to environments of ints, sort of the default semantics. This is actually just syntax. So if we wanted to get this to work, I could say ends int.run, and then provide a number here. So I'm going to provide, I guess, 55. And when I run this, now we'll see hello Func Prog Sweden, 55,000. And if I change that number, it'll change the result. So whatever number we put in here is what's going to pop out the other side. And so if I'm going to pull this out here and call this val handled ends, and give this a type signature, put this back in here. And we're going to see that by running the environment effect from our initial program, we've sort of eliminated that bit in this type signature. So this thing here to the left of this less than sign, which is sort of, I think that the term for this is pending. So it's an int pending these effects. So this is a list of pending effects, a type level set of pending effects, essentially, by using the intersection operator in Scala. This is just listing the effects that are in your program, and as you can see, it's perfectly inferred based on what you use here. So if I don't use the consoles, it will not show up in this list. But if I do use it, it will show up. And this tracks what we need to handle before we can actually finally get the final result of our value. So we have to handle these one at a time, first handling the environment, and then we can handle the console. We can do other things as well. So let's look at another interesting effect here. One might be the aborts effect. So I'm going to say aborts of string, and I believe there's one called when. So if the number is greater than 100, I'm going to say, number is too big. And this fails because the type is wrong now. I have to re-infer the type, or I can if I want to. And for teaching purposes, I'm going to infer the type. So we can see that now it depends on consoles, an int in the environment, as well as this ability to fail with a string if the number is too large. And so I'm going to make this 99. I'm going to actually move this back down here because we get the idea of eliminating things. And now I'm going to have to say aborts string dot run, and just I'll wrap it with that, and everything compiles now. And now it's actually going to return a write of 99,000. So these different interpreters can actually change the result value. So we have to deal with the fact that this might fail and short circuit if the number is greater than 100. And therefore, we have to transform the resulting value to an either of a left if you failed or a right if you succeeded. So by running this aborts effect, it's going to transform the final result type that's returned from this bit here. Cool. And we'll do one last, well, let me actually make this a larger number so we can see what happens if it fails. And we're going to see it's left 199 is too big. And that is indeed going to short circuit. So if I say goodbye, Func Prog Sweden, we will never see that value if the number is too large. But if it is a decently sized 99 there, we will see both of the print lines and it will execute correctly. The last effect I want to show, just because it's pretty cool, is the ability to have non-determinism or branching decisions, the sequences effect. So what I can do here is I can say, I don't know, multiple, and I will say seeks.get, and I'll say 1 to 5. So we'll make a range from 1 to 5. Then I'll map over that range and multiply our number by that multiple. And then this will change the type again. Now we're going to have aborts, consoles, environments, and then also sequences. So we get that in there. And then I will simply just actually return multiple here at the end. And I will check to see if any of the multiples are greater than 100. I will say that the multiple is too large. And now we also have to deal with sequences. So I'll say sequences.run, wrap this whole thing. And I'm going to make this into just the number 10 here. And we see we actually get now a sequence of 5 values, one for each multiple in here. So this is sort of like the list monad, if you're familiar with that. It allows us to extend in this beautiful composable way our Kio effect, this algebraic effect, with the ability to do this sort of very complicated form of comprehension. And if any of these fail, so I'll say no, I'll change the number to be larger. So I'll make this 22. We'll see that 110 is too big. So 22, 44, 66, etc. And if I make this larger still, well, larger still, now that the top two are too large. So we get a list of eithers. And we can actually change this by swapping how we run, what order we run these effects in. So if we first run the sequences, we'll see that actually, if any of them fail, we're going to get a left of the first failure. But if all of them succeed, we're just going to get one right of all the successes. So it's very modular. If you're familiar with, I guess, monad transformers, you can play with the ordering of those things. But yeah, it gives you a lot of power, and it's sort of this beautiful way of just adding non-trivial behaviors, capabilities to your programs in a very composable way. And it can do a whole bunch more. It can do forking and concurrency. We're not going to take a look at that today exactly. But I just wanted to give you an example of the API we're sort of shooting for, though I'm not sure if we're going to have time to get to everything. For instance, this type level set tracking, though I will mention it later. Okay, so that was our Kio example. And now we will write that from scratch. We're going to write the Kio from scratch, basically, starting from very much the beginning for babies. And I include myself amongst the babies. So we will begin with a very simple DSL to get the hang of this. So going back to, and I might need to be sort of in the corner because of all the text. No one needs my giant face. A small face is tolerable. Thank you. So we have a simple a DSL here that we're going to start with. And this is very much like what we looked at before by creating a syntax tree for a trait. So imagine we have this console trait. Keep it really simple. Read line, print line. We can get a string from standard input, right to standard output. So if we wanted to create a DSL out of this, we might start by creating an abstract syntax tree for this trait as a way of building a functional effect for this thing. So we'll make an enum called console, and have a case for read line and a case for print line. Yippee, read line, print line. And print line, if it had a parameter, a method parameter, that would turn into a case parameter, a constructor parameter. Pretty straightforward, hopefully. And then separately, we can define semantics for this syntax by writing a handling method that will accept the syntax, match on it. If it's read line, we can actually defer to the, oh yes, read line and print line. We have to deal with both of these cases. If it's read line, we will actually read a line from the console. And if it's print line, we will actually print a line to the console, delegating to the Scala standard library functionalities. We could have other handlers as well, which returned dummy data, always returned the same name and didn't actually write to the standard output, but wrote to some, I don't know, mutable list somewhere, or did something else entirely. But these are one set of semantics, maybe the default semantics for actually using a live console. And so then we can run this by constructing a piece of syntax and then immediately interpreting it. So if we handle constructing a print line node, we will see who are you printed to the console. Not terribly useful yet, but it gives us the general idea. We have syntax, and then we interpret that syntax directly. So there's that severing of the syntax and the semantics, unlike, say, when you define a method in normal plain Scala, where they're sort of bound together. Every time you define a method, you both define the syntax, as well as often you have the equals and the actual method body. And then we can subsequently handle read line. And then we can also print a fun message out afterwards. So we have to handle these one at a time, but nonetheless, the basic most DSL is here. And technically it works, as the text says over there, but we have some issues, and we were going to look at the types to see those issues. So one question we could ask ourselves is, what is the type of name here? We've handled read line, and intuitively, we might think that, oh, that should be a string, right? We're reading a line off the console. But what does handle return when we pass it a read line? And well, in this case, standard m.readline will return a string, but print line returns unit, and therefore it's going to find the least upper bound. The Scala type checker, type inference system, is going to find the least upper bound of string and unit, and that is going to be any, sort of the top of the type hierarchy, because there isn't any reasonable supertype beneath that string and unit share. And therefore name is any, which really stinks. Luckily or unluckily, depending on your perspective, Java does have a two-string instance on any, so it'll still get string interpolated and render correctly. So everything did seem to work, but this isn't very type safe, doesn't feel very good. Building an untrue program out of this would be an immense exercise in masochism. Scala 3, however, also allows us to use disjoint union types, which is nice. So we could constrain this a little further and say, well, it's either string or unit, which is cool. However, that doesn't really help us implement it. We could still call print line in both cases. You know, unit in both cases is still a subtype of string or unit. And either way, this thing is still going to be a string or unit, which is just like, we don't want name to be string or unit. We know it should be always string if we handle read line. We want this to be string. So how do we fix that? And similarly, of course, we want print line to return unit. And so this is where we can use GADTs. So GADTs, if you're not familiar with these, it's a mouthful. It's fun to say. It stands for generalized algebraic data types, but it's actually pretty simple of a concept and very powerful. Highly recommend using them. And so we're going to look at this next. It's really just a fancy way of saying, let's add a type parameter. A type parameter in a specific place for a specific purpose, giving us specific powers, type inference powers. So get it, slideshow. All right, so back to our code. We have our read line, both definition and our trait, as well as our syntactic read line case. We have print line. We've dealt with these. We've dealt with the arguments, but it turns out we actually didn't ever handle the return types. We didn't really represent these in our syntax tree. And if you're writing a dynamic interpreter, you don't necessarily have this information at compile time. But we're writing an embedded DSL inside of Scala, and it would be really great if we can use Scala's amazing type system to help us, so we don't have to write our own compiler. If we can use Scala as our compiler, this embedded language that we're building. And we can do that by making console here into a generalized algebraic data type. So we're going from ADT, pinning a little g on the front. And what that means is we basically just add a type parameter to our trait or our enumeration. And this represents the return type of this syntax tree. So once again, this is just syntax, so it doesn't actually mean return type yet until we handle it. But theoretically, concretely, if you are using this to build a DSL, that type parameter you're adding there, you have to add one that represents the theoretical return type. And therefore, readline, to say that our case readline returns string, we're going to make this extend console of string. So it's a bit more verbose of syntax, yet this is how we're going to express that readline is a console of string. It returns a string. Whenever you see extends console of whatever, that whatever in there is the theoretical return type of this computation, this DSL. So similarly, for println, we extend console of unit, because println should return unit. And now the beautiful thing is we can use that. So right now, console needs a type parameter. So we're going to have to add a type parameter a here. And therefore, we're going to have to introduce it to our type signature. And what we can now say is instead of returning string or unit, we want to return the return type of whatever that console is. So this is sort of this phantom type parameter that exists to mark certain cases with their return type. And now we can say, well, if we handle one of these cases, we want it to return, the implementation better return the type that we've annotated here. So readline, if we come across this, the Scala compiler is actually smart enough to know that when you match on syntax and you see it's a readline, well, it knows that readline is a console of string, and therefore it can figure out that, well, then a must be string. So in this case, we have to return the string, and therefore this compiles. And similarly, if we were to not return string, it would be a compilation error, which is pretty great. It helps us constrain our implementation. So we couldn't screw up like we could before and return println here. Or when it was any, we could return literally anything. Now we're constrained. Very nice, helps us implement our DSLs. Similarly, with println, it knows when we match on println is of type console unit, therefore a must be unit. We have to return a unit. It figures it out. Encoded, I don't know how the compiler does it, the type checker does it, but it does. Some kind of, constraint solving, good for them. It works really well in Scala 3. And we can't, of course, return a string here. It has to be unit, which is returned by the default println implementation. So the next problem was when we called handle println, we didn't get unit, we got any, but now it will actually infer. We get that for free as well. So now what the type checker is going to figure out is, okay, you've passed in println to handle. Println once again is console of unit, therefore a is unit, and therefore what we're getting out of this handle function must be unit. Similarly with readline, the same logic will occur. And yay, API perfection achieved, at least so far. Of course, there are still many things we have to fix. So we're going to keep solving problems, introducing more problems until we run out of time, probably. So let's see what happens. The next question we're going to ask ourselves is along the will it blend line of reasoning, will it compose? And I should have said will it blend, because that works for composition. So anyway, one ugly little blemish here on our DSL is that we have to immediately handle our syntax. Each time we're constructing the syntax tree and then we're handling it. It kind of feels completely pointless. Like, why did we build this syntax tree? What are we really gaining here? It's very limited powers. So we print it, we handle it. Yay. This greatly limits our DSL, and it's not really composable. We just have these leaf nodes. We just have println and readline. There's no operator which allows us to combine these together to build larger programs. That's the beauty of functional programming, is that we get to build these compositional DSLs where we can have this simple set of primitives, and with the combinator, we can just exponentially grow and express really complicated, powerful ideas from a set of simple primitives. But we have no means of achieving that combinatoric explosive power. We have no combinator. So to guide where we want to go with this, the present is this, pretty ugly. We have to handle each time. It's basically side effecting. We have no composition. Ideally, syntactically, at least, we would like something that looks like this, like normal direct style, because, you know, it's simple, it's minimal. If we could achieve that, that would be great. The compromise is going to be in Scala, as in Haskell. You have to, if you wish to maintain your program being a value, you're going to have to use some kind of syntactic sugar. In Scala, it's a for comprehension. In Haskell, it's do notation. And this will allow us to maintain the property that we want, which is that this is going to be a pure value of the syntax type. This whole thing is going to evaluate to one syntax node, yet it kind of looks like direct style, at least as much as we can achieve in the languages of today without macros. And Kio actually does have macros that allow you to write literally something like this, but achieve that first property of it being a syntax type. So that's pretty cool. But today we're just going to look at this. So this is still going to be a console of unit. Ideally, we have to add this to our language, but this is our next goal, to make this code compile. How can we do this? And then, of course, we can handle it once and only once at the end, instead of having to interleave our handling, basically defeating the purpose of having our program as a value if we have to implement every new line with the handles. It's worse in every way. Of course, there's still the blemish of the syntactic constructs here, but we have to deal with that. So let's implement the compromise. And let's achieve sequential composition. So bringing back some of our code here, we have our enumeration of our syntax console, and we have our handler, our semantics for our console syntax. And then we have this program that we wrote before. And to incrementally achieve what we're going for, we're going to work in baby steps here. Let's try to get this thing to work. So the idea here is that instead of first handling print line and then handling read line, we're going to construct a sequence of first print line and then read line. And then this is going to return some kind of console, which can then be handled all at once. And the semantics that we want is essentially for it, because this is not semantics, it's just syntax, but generally you create syntax with some semantics in mind. They kind of inform one another. We would like this to theoretically first execute the thing on the left and then execute the thing on the right, returning the result of the thing on the right. So do this, then do this, return whatever this evaluated to. And that's why this would hopefully return a string here and not unit or some combination thereof. So console string is what we would want from that type. So how do we implement this? Let's add some syntax for sequence. So we have this sequence node. Let's create a sequence node in our enumeration. On the left-hand side, we have another inductive call, a recursive call to console. So we have some other node of console. In this case, println is of console type unit, as we've seen before, but we really want to be able to sequence any two consoles. So we can add a type parameter and say, yeah, any A will do. Similarly, on the right-hand side, we have a read line. And while that's a console string, we want this to work with anything, console B. And then the return type of this, we want it to be determined by the thing on the right-hand side. So we could say extends console of B, right? Because the console of string is determined by read line. Read line is the right-hand side console of B. We want this whole thing to return a console of B. And there's nothing wrong with saying that this should extend a console of A, except then we would have to implement different semantics, at least for this one handle. And that's not what we want in this case. Okay, so that's the syntax part done. Check, thumbs up. We have syntax for console. Next, we have to actually implement handling for this, because right now it would be an error once we came to that sequence node. So let's give sequence some semantics, very sibilant today. Case sequence. So we have to handle this case. And basically, we just first handle the left-hand side, and then we handle the right-hand side. And the right-hand side is a console of the right type. So when we handle that, recursively, we'll get its value out, and that will be what we want. Yippee. So a pretty trivial implementation. And if we run this, it will indeed work. First, we'll see who are you printed, and then we'll see an input sort of prompt. Or rather, we'll have to type in before the program continues. And that will return whatever we typed. So, yippee. Solution solved, new problems introduced. So The next thing we want to do is threaten our user. So we've gotten their name, and now we can use that name against them to wage personal insults against them. So we want to then handle print line, your days are numbered, whatever your name is. A personal message is very touching to people. So unfortunately, we are not able yet with sequence to access the result of a previous computation. So we want to sort of get the result of read line here and be able to thread this along to our print line without having to first handle everything that came before it. So we want to access the result of sequence without handling it. And so perhaps we can come up with this syntactic structure, which is like sequence, except a different node. It's called and then, we'll call it for now. On the left-hand side will be any kind of console computation, syntax node. And on the right-hand side, so yes, first we're going to execute sequence, and then whatever the result of that console type was, in this case a string, is going to be the argument to this function from which we will generate a new console. So that's the syntax and sort of our idea of the semantics. Okay, so let's do this. Let's add some syntax. So, and then node. This has two arguments. The left-hand side is going to be some arbitrary console of type A. The right-hand side is going to be a function. So we'll just get some kind of function type in there. The input is actually going to be the result of the output types. That's going to be A. And the output is going to be some other console of some other type as well. And then we want to return, just like in sequence, the final resulting type of that right-hand side. Behold, and then. Cool. And now for semantics. And these are going to be a little more complicated than sequence. And just to practice some parametrically polymorphic reasoning, pibilant. I don't know if there's a plosive, I guess would be the equivalent of sibilance for P sounds. Anyway, and then semantics. I'm going to talk about here some kind of, I don't know, semi-mechanistic logical reasoning tactic that you can use when solving parametrically polymorphic methods, because it also often does feel like solving a puzzle of some sort. And there are some, I don't know, intuition hacks you can use. So I like to cycle repeatedly, recurse between these two questions that I ask myself. The first is, what do I need? What's the goal here? That's often determined by the return type or the value you're shooting for. So in that case, it's going to be the A. We need to generate an A from this function. So a value of type A is our current goal. And then once we've established our goal, oriented ourselves in that direction, we can ask, what do I have? What's in my inventory, if you will? And that's going to be determined by really any identifier you have access to in the standard library or anything, but we're going to scope it down in this case to, okay, well, we have a left-hand side that we've matched on, and we have an F that we've matched on, these two properties contained inside of the and then syntax case. The left-hand side is a console of type A. So we could say we have a console of type A here. However, and this is where, you know, if you're new to this kind of stuff, it can get a little tricky. Technically, this A is not the same as this A. So these are just type parameters, A and B and whatever. And what matters more is actually what position they're in and whether or not they show up on the right-hand side here. So it could be a little tricky. I'm going to do some re-aliasing. So in and then, our return type is actually this B, but this is just a name. We could have called this whatever we wanted. We could have called it Kevin, but our return type is Kevin or B. And that Kevin or B is determined by the result of F. And the input to that F is A, which we actually do not see here. It's sort of this internal type that is not viewed on the outside. So the result of F determines the result of and then. And this A is different. So the A on the outside is not the A on the inside. The A on the inside is actually what is sometimes known as an existential type. It's some kind of type, but it's not present in the external console type. What the Scala compiler will know is that and then will contain some type X, a console of type X, and a function that'll take that type and return a console of the resulting type. But from the outside, when we know that this is just a console of type A, we actually don't see the X at all. It's existential, it's hidden. It might be a little confusing, but it's something you have to get used to. Hopefully by renaming this, I'll rename console of B to console of A. We won't have to do the mental mapping, but that is something you will have to doing these things yourself. Probably the biggest challenge, keeping track of those things. Okay, so the left-hand side is actually a console of X, a console of some type that we just do not see here. We do not have a type parameter for that type. It's going to be internal and hidden inside of the and then node. And then we have F, which will, of course, take that X to a console of A, which is what we want. So that's our inventory. A brief aside on existential types, probably slightly confusing, I apologize. But that's our inventory. Don't worry about that if it was a little crazy. X is an existential type. Oh, thank you, note for myself in case I forgot to use that buzzword. Okay. And then we actually also have access recursively to our handle function, our handle method. So we can also add that to our inventory. And handle is essentially a function from console of A to A. Except once again, not the A that we were talking about when we were dealing with this just a moment ago. Handle actually works on any A. Handle is generic. It has a type parameter. So for any console of some type, it will return that type, which is a little confusing. So I will use a lowercase a here to just denote that handle can really just unpack the result from any console. That's its magical power. And we can recursively depend on that. Okay. Now that we've gotten through that, we need a value of type A. We have these three things. We can just write this code here as dummy placeholder code. We're going to return an A. Yay, it compiles. And A, okay, we don't know how to get A yet, but we have A. Let's pretend. So we return it. So the next question is, of course, how do we get A? That's our current goal. And what you could do is you could sort of browse over your inventory and just look for that type. Because A is a type parameter, we cannot pull one out of thin air. It's not an int or a string. We can't just return 0 because we know it's an int, which might not be correct. But by having this parametrically polymorphic, this type parameter, it constrains us in a really neat way, where we sort of have to look towards our inputs to get it because we know nothing about it. And so the only place it shows up is as the result of this F type. So we sort of know that we have to get it out of this console somehow. That's the only place we can get an A. And furthermore, we can only get that console if we call the function. But for now, let's just focus on this console. And we can once again pretend that we have a console of A. Let's just pretend we have a console of A. It's clearly accessible somehow. We'll worry about that later. Now we can add console of A to our inventory. We've made it up, sure, but it's there. So if we have all of these things, how do we get an A from a console of A? And so our solution in this case is going to basically be a function from our inventory to our goal. So we could use this function type sort of as a reasoning tool. One of my favorite parts of functional programming is just like a really nice reminder of this logical sort of proof-solving pattern. And in this case, concretely, we want a function that goes from console of A to A. And luckily, we kind of have that in our inventory. The handle function goes from a console of any type to its actual contained value, which means to get an A out of a console of A, we just simply recursively handle that. Yippee. Okay. And now our goal changes. So instead of needing an A, we recurse. And well, we have these question marks here that we created a moment ago. We now need a console of A in order for the program to continue along. We're sort of burning the candle at both ends, starting from the end and working backwards. It's a nice way of doing things. And then we can also switch and start from the beginning, drill down from the top and the bottom, and try to meet in the middle. But we'll keep working up from the top. So we want a console of type A. And we can, once again, peruse our inventory and see that, yes, well, that same F contains a console of type A. But it's locked away in this lockbox of a function. And in order to access its contents, we need to provide the input, which is, of course, of type X. So give input, get output is the law of functions, which I've made up here. So we could call f of X. Of course, we'll need an X now. So we could just pretend we have an X, and then, yay, we have a console of A. And we once again recurse. We now need a value of X. How do we get a value of X? Let's peruse our input. What do we have? Well, I see an X there inside of a console. So once again, it's just as we did before. We can use the handle method to unlock the X from our console. So we'll handle the left-hand side, which will get us an X. So we just cycle between what do I need and what do I have over and over and over and over again. And finally, we go from our inventory to our goal. We can just combine a bunch of these reasoning steps together and have a function from input to output. And we finally get to collapse it a little bit, this code, where first we handle the left-hand side, get the x out, then we call the function with the x, which will get us a new console out, which we have to then handle to return the final a. I broke that down probably into too much granularity, but we're going to use that same reasoning logic later in a slightly less trivial scenario. Hopefully that was useful. Okay, let's take a sip of our LaCroix. Delicious. Okay, continuing along. We have sequence and we have and then. This is a bit of refactoring. These are almost identical. The only difference is and then accepts an argument which can be used to determine the next console step. So really what we could do is we could change our implementation here of sequence to just simply use and then, but then just ignore the result of the left-hand side. And if we do that, we can just kind of delete sequence. So it was a nice maybe baby step to the complexity of and then if you're new to this, but beyond that, and then is strictly more powerful than sequence, so we can implement sequence in terms of and then, and we can get rid of this. Next, slightly nauseated by obviously just constructing raw syntax nodes, but that's no problem. We can just define some methods. We have types here. We can define some methods that are rooted on the types. And so instead of constructing an and then in this way, we can instead make it so that we can dot chain and then onto any sequence node and improve this slightly. So we'll do this. And how do we do this? Well, we define a method on console of A, and it's going to look very similar to our type signature before for and then, except we are only going to have to provide the f, because when you define a method on a type, you implicitly have access to this, which is sort of the underlying console. So the left-hand side becomes this, the one that we're defining this method on. So the definition we can have is just and then pass in ourselves, right? Pass in print line as the first argument instead of explicitly doing that. Same idea. Cool. And that will return a console of B. And yay, we now have and then, and we can chain these together below, as we did here. So now we can just rewrite our program in this one dot chained syntax, and it looks a little better. And I'm sure many of you, this is from Prog, so I'm not sure if I'm being coy or clever or anything, but generally, and then is known as flatMap, because you're sort of mapping over the value, but producing another type of the same kind, and then you have to sort of crush that down, I guess, is the reasoning. You don't have to worry about that reasoning. Just know that flatMap is what gives us this mode of sequential composition. The same thing as and then, just a different name. So we will now use flatMap from here on out and try to stick to real words. Cool. And now we can just also, oh yes, one last thing we need actually is, what if we wanted to sequentially compose with a value that was not in our enumeration? So just we wanted this to actually return, instead of a console of unit, which is the result of print lining, and instead of read lining, like right now we can only read line or print line. What if we also wanted to just be able to return a normal Scala value, right? We're using this embedded DSL in Scala. Wouldn't it be great if we could just embed any kind of Scala type inside of our DSL? That would be quite convenient, if nothing else. So we can't quite say flatMap this, and then just put a string in here, because a string is not a console of B, which is what we need. So it'd be great if we could make another case of our enumeration and just call it value. And the purpose of value is just to hoist any arbitrary Scala type into our into our type system, into our syntax. So we'll do that. We'll create a case called value, and it will just lift any old A into our console. Pretty trivial. And then we can handle that just by unwrapping it. Yippee. Fairly simple semantics. If we see a value of some type, the semantics are we just give you the type that was, or the value that was inside, nested away. Okay. So we have that. Okay. And then instead of doing this flatMap, we could actually maybe make a new method called map, which didn't have that sort of unnecessary nesting of our arbitrary Scala type in this value constructor. And the definition of map could simply just take a method from A to B, a function from A to B, and just do that same thing that we did before. We'll just flat map over this and then nest the result of that transformation inside of the value. So we're just abstracting that ugly thing that we had into the slightly simpler syntax. And this will get us a console of B. And huzzah, what we've done is we've created a data type. What we've done is we've created a data type, a method called flatMap, and a method called map. And once you've done that in Scala, you have then given your type enough power to work with for comprehensions. So now we can, instead of writing this, we can simply write a for comprehension. And this will work magically out of the box. Because for comprehension is simply syntactic sugar. And what it does is for each of these lines, so here we have this underscore backwards arrow thing, the unnamed mystery binding arrow. For each of these, what it's going to do is it's basically going to rewrite it to be a flat map. And the thing that was the underscore is basically the argument to a nested closure, a nested function value. Similarly, for the next line, name is going to get shifted over there as the argument to flat map on read line, once again nesting. Do that once more. And then the very final time before the yield, it actually turns into map. And then the value of the yield is just sort of the raw value. So that's kind of how the desugaring of the for comprehension works. So if we go, oh yes. And the cool thing about this is that because these are all nested, which is quite horrific to look at, but because you have this callback hill, any parameter, any function parameter you introduce can be used in any of the subsequent nested function calls, because this is going to be in scope, both for print line, but also for in here. So we could use name in print line, but we could also use name if we wanted to in our final value. So that has sort of similar semantics to just normal direct style line by line code, where identifiers you introduce, vals you define, variables you define on one line are accessible on subsequent lines. And we get sort of a similar aesthetic syntax semantics duality here with that. So if we translate the other way, now we can have a for comprehension. We take our flat map, the argument just becomes the name to the left-hand side of the arrow. Flat map name becomes the name to the left-hand side of the arrow. Map becomes the underscore there in that case. And then the final value becomes yield. And once again, it looks just like direct style. We have access to name on subsequent lines, quote unquote. However, under the hood, they're actually just all nested closures. But even with direct style code that you write and it looks like it's sort of existing on subsequent lines, that's just syntax. Like the actual compiler will turn it into machine code where there's a stack and it's completely different. Like it's not actually available on subsequent lines. It's this actual underlying semantics as it's translated to machine code are completely insane and random. So the idea of translating this to a series of nested closures in this continuation passing style is not any crazier or any more magical than what the actual final compiler is doing. And that's for comprehensions, yay. So we've achieved that goal. And name can once again be read on subsequent lines. To recapitulate, because of course we're running out of time here, and so we should definitely waste time on recapitulating. We've created a simple console DSL. We've upgraded, so that's that one, with no special types. We had some type inference issues. We then extended it to a GADT by adding a G on front, and also adding a type parameter representing the return type. And then we finally outfitted our DSL with sequential composition, which is great because now we can build larger programs, but keep them inside of our DSL type here, our syntax tree, and build a giant syntax tree and handle it once at the end instead of having to handle it in this interleaved manner, line by line, basically being completely pointless. So what do we want to do next? The next thing we want to do is to add potentially additional operations. Right now we just have print line and read line. But what if we wanted to add a method for getting the time that might return a local date time, or like that environment method that we looked at previously in Kio, or so on and so forth until the heat death of the universe? Well, currently we would have to add a whole bunch of cases and then also handle a whole bunch of cases. which isn't the end of the world. This is how other functional effect systems work, kind of. They have one mega enumeration, and they have one mega handler that does everything. But the beauty of an algebraic effect system is that it's composable and modular, and it can be sort of broken apart so that not everything has to live together in just one giant enumeration. There's not just one syntax and one semantics. You can actually compose different groupings of syntax and semantics in an ad hoc fashion, in a user extensible way even, which is pretty cool. So our algebraic effects should be arbitrarily extensible. So what we want to actually do to just drive towards this reality is, let's take print line and delete it. Let's take read line and delete it. Like, this that really core to the algebraic effect language. That's, you know, a console domain. And then we want this ability to actually embed arbitrary effects into this this algebraic effect domain. And that's going to be the next goal. How do we let anyone embed their own effect into the system without having to actually add a case for each of those n cases for n different operations? We want one case that allows the embedding of any operation inside of our DSL. And we probably shouldn't call this console anymore, because it doesn't make any sense. And for lack of a better name, I will call it Kio, in homage to the inspiring library by Flavio. So we'll now call this Kio. Hooray. And we can now break apart our console into its own little syntax tree. So we get this modularity. We can decouple, sever these from each other. And the idea would be, it can have its own semantics, its own handler just for the console. And we can have our own sort of top-level handler for dealing with the mechanics of sequential composition and the embedding of arbitrary other operations. And somehow we need these to fit together. We need to take the chocolate of Kio and the peanut butter of console and have a horrific car accident. Okay. A Cronenbergian abomination must be created from these. So how are we going to do it? And once again, we would like this to work. So a program where we can first read a name and then I've always loved you. And we've gotten sweet at this point in the talk. And this is going to, once again, to de-sugar it, be a flat map. So you see this for comprehension? The flat map is going to first be a flat map of read line, and then take the continuation here, the results of read line, and pass it along to create a print line node. Obviously, there's a problem, which is that flat map is of type Kio, and read line and print line are of type console. So this will no longer compile. This will no longer work. We need something here to wrap console in a way, to embed console in our language, if you will. And so if we do this, we can embed read line and then embed print line. Well, now the syntax part will compile again. This isn't the end step, but hooray, we're working towards something. And this should return, the return result of embedding a particular operation should be the return result of that operation. So we'll just have embed return A, the A determined by whatever the console's A was. And of course, we don't just want to hard code this to console again. So that's convenient for this transformation, getting everything to compile, but we want this to work with any kind of operation. Like this would work right now. We could just match on op and then handle console op with that op. And like we've just basically added a whole bunch of syntax that does what we did before, except we've kind of arbitrarily broken these out into two different hunks of code, but it's really the same. It's doing the same exact thing. We want this to work with any operation of A. Unfortunately, that is not a type, so we have to add a type parameter here. So for literally any type that has a return type in this sense, this should be able to work for. And so then we can match on embed and do something else. Okay, I might need the rest of the time. This is definitely a lot of stuff to talk about. I will abort at some point, but there's a little more juice in here. So we have this operation, and we don't even know what type it is. In fact, this will not compile because this operation, just like the existential type before, from this A in flatMap, operation does not exist in Kio. We don't know what this is. All the Scala compiler knows is that, hey, there's some higher kind of type here, operation that's parameterized by A, but I don't know what it is. It's something. So let's focus in on this problem. And using the same technique, the technique has reared its convenient, useful head again. So first we can ask ourselves, what do I need? What's our goal? And the goal is, of course, an A again. So we can bootstrap ourselves through this and say, okay, we need an A. How do we get an A? So we ask ourselves, what do we have? Well, of course, we have an operation of A, and that's all existential, or the operation type is existential. There is no type. We don't know what that is. And so what we kind of need in order to do this is we would need a way from going from operation of A, our inventory, to our goal, which was previously A. And so it would be great if we had one of these things in our inventory, but we don't. There is no operation of A to A. So we would be doomed usually, but luckily we're actually building this whole thing from scratch. Like there's no constraints on this. This is our library. And so we can rejigger anything we feel like at any point. So we can summon this from the depths of the void, void in Haskell, I guess. Nothing in Scala. We can summon this from the emptiness of all existence and simply add it to our type signature. Yay, which sort of feels like cheating. So we'll just add this handler type here. So what if we did have, in fact, a function from operation of A to A? That would be great. And then yay, we have it now. So let's simply call the thing that we just summoned to solve this particular problem for us. And everything compiles, yippee, sort of. There are a couple problems here. One is that, of course, this is a type that doesn't exist. So we'll have to add a higher kind of little type parameter here. I'm going to call it op. The name doesn't matter, but to save on horizontal space instead of operation everywhere, call it op there. So now this still will not work. Operation of A to A, because we can imagine this situation where we first, so we have this kio of unit, and the first operation is inside the flatMap. We're eventually going to get to this embed of read line, which is a kio of string. And the second one is a kio of unit. And these are different A's. But where this A is introduced is around the entire handle, so which is determined by the result of the program passed in. So A is going to sort of be hard-coded to unit. Therefore, we're going to have to pass in a function from operation of unit to unit. And that will not allow us to handle the string case. So we need this to be more flexible. We need this to be able to take, just as sort of before, any operation of any type and get the type out, no matter what that type is. So we need to make this sort of a polymorphic function. And we're going to do that by introducing another trait called handler, which is going to have this apply method, which is that polymorphic function. This will basically take, because this is parameterized by A, it's sort of at a tighter schedule, at a narrower scope, this can be called with any operation of any type A, and it'll just get that thing out of there right away. And so we can, yippee, basically same thing almost, except in this case, the A is introduced right where we need it. And here that A is sort of introduced at the too high of a level and is going to be bound and sort of rooted down, nailed down by that, whatever program you pass in. So, of course, we need to add that op type parameter here. And now we can put in handler here instead of the apply. And this will actually, well, almost work. The other problem is we're referring to this operation here, which doesn't exist. So for now, we're going to, because this is basically an existential type. And if you do command hover your mouse over op, you'll see a little $ inserted in front of it. And that's just the Scala's way of representing an existential type. Like it doesn't know what operation is. It's this thing that's just kind of packed up inside of the embed node. And it's something that wraps an A. We don't know. So we can just remove that type description and just say this is an op. The problem is, of course, that handler is a handler of a particular operation type. This cannot deal with every operation type. It has to deal with a single operation type. And we cannot abstract this any further. Like the handler needs to know about the operation it's handling. Otherwise, it can't handle it. So it needs to be a handler of consoles, a handler of time functions, etc. And so simply what we can do is just cast the operation as an instance of operation of type A. For now, that'll work. And it's ugly, and there's some type safety problems, of course, but we're sort of just in these intermediate stages. And then we can define a console handler to be a new handler of console, and its apply method will take a console of A and return A. And it'll just do this thing that we were doing before, except now it's inside of this little convenient handler type, which allows us to have this essentially a polymorphic function. And so now what will happen if we walk through this program is we're handling the program. I'm just probably going to go up until time. I'm just going to go up until time because I've made too many slides. what a crazy thing I've done. Okay, so we're gonna handle this program. And first match on the flatMap node. And of course, the Kio is this embed. And therefore, the first thing we're going to do is recurse with embed of readline and our handler, which is the console handler. So then we've recursed. And now we match on embed of readline. The operation is readline. And then we call the console handler with readline, casting readline to a console type. And then basically it's going to match inside of the handler on readline and read a string from standard input, which will then be returned from the embed case, the embed handle call, which will basically set x equal to that string read from the console. And then we have f, which is this function that takes a string and returns an embedded print line. And then we're going to call f with our string, getting us back an embed. So then we're going to basically handle this embed where the name here has been interpolated to be whatever was returned from the read line. So we recurse with embed print line of whatever, and then we're going to come to the embed case. Once again, the op is print line. We call the console handler with print line. We'll match down here. We'll take that string, print it to the console, returning unit. This returns unit. This returns unit. And that's the end of flatMap. Hooray! We've walked through our program. And it works just as before. We've broken down a handler and all this stuff. Every time we solve a problem, I have to undermine our solution. And so first, let's one more recap. Previously, we had this all-in-one enumeration. But the idea of the algebraic effect system is we break it apart and have a means of embedding arbitrary operations into our effect system. And we do that for the syntax. And we also do that with the semantics by previously was all in one sort of interpreter, handler, which provided the semantics for our whole program. And now we break it apart into a handler, a semantics for sort of the overarching effect system, the Kio, and then individual handlers for individual operations, which we can provide one at a time, which is pretty powerful. But we have more problems, of course. Of course we do. Firstly, it's a little weird that we're just casting any operation to the operation of the handler. For instance, what if we had another operation like random, which gets us random ints and random doubles? And then it could have its own handler that would match on those and delegate to Skull as standard libraries means of procuring those values. If we use these in our program, and we had these, like imagine there's some companion object with these methods that just, we don't have to construct those syntax nodes. Def next int will just embed the syntax node for us. So this is just a nicer syntactic layer for us. So we could call random to get an int and then print that to the console. Now we're using two different operation types. And if we were to try to handle this, we would, with the console handler, we would eventually come to the flatMap. Well, we'd first come to the flatMap node. Then we come to our random node. We recurse on embed random next int, which would get us here. The op would be random next int. Then we would call console handler with random next int, casting it, of course, to the type of our console handler's operation, which was console. And this would explode. Cast random next int to console. That's bad. So this is not quite going to work. We should only call the handler if it can handle the operation. And once again, we're constrained, so we have to extend our library in some way. And so why not just add a method to the handler, which says, hey, can you handle this thing? And it could return a Boolean. And then on our console handler, we could just say, okay, if the operation is an instance of console, then sure, we can handle it. And so what we have to do here now is we can add a guard condition saying if the handler can handle the operation, then, well, we can safely cast it. But if it can't, no, shoot, well, then we have to figure out something else. And there's actually nothing we can really do about this. Once again, we're limited. We cannot interpret, we cannot get the A out of an operation that we don't have a handler for. Like if we get a random embed of a random node, how are we supposed to fulfill this type signature? And the truth is, we just cannot do that. We actually have to keep it embedded, which means that we cannot return an A. There's no safe way that we can really work around to get this type signature to work. So this actually has to remain a Kio of A. which is sort of similar to when we were looking at real Kio before. We just sort of are eliminating these effect types, but once you've eliminated all of the effects, you get it would look something like int underscore any. So the type system, if we had this ability to track these things at the type level, which is sort of another problem, and you could do it, you would know that there are no more effects to handle. So you can get around this problem that way. Don't have time to get into that, unfortunately. So we're going to have to keep things inside of our Theo type here. Which means also this is a problem. So we're actually going to have to wrap this result in a value, because otherwise we would just be getting the A back. And similarly here, this is now going to get us a Kio of X instead of the X type. So it's a bit of an awkward thing. What are we supposed to do here? And I'm going to go 3 times speed just for the end. Yeah, we need to call F takes an X, not a Kio of X. So to make this a little simpler, we can actually rejigger our enum. You know, you always have the option to return to your core syntax and constrain things. And it would be slightly more convenient to do the next thing we're going to do if, instead of this being a Kio, which could be either a value or an embed or a flatMap, if we always knew this were an embed node, that would make things slightly easier. And we can ensure that by changing our definition of flatMap to match on the current node. If it's a value, we can simply call the F on the value, sort of eagerly unwrap the value and call F on that A, getting the key of B. If it's an embed, we can sort of do what we did previously, just nesting that in the flatMap code. But if it's a flatMap, we can extract the embed that's in there, put that on the, keep that on the left-hand side, and then basically first go from that initial sort of existential X to A with calling that first function on it, and then flatMap on that resulting A with our new F to get the key of B and nest this all up in there. A little interesting. So we just kind of make sure that this is always trailing off on the right-hand side. So now if we know this is an embed, I'm going to end in just 1 minute. Then we can check to see if the handler can handle the embed. And if it can, then we can handle it with the handler. So just as we did in this instance, and then we get the raw X value back, and we can simply do what we did before, because this is no longer a Kio of X, it's just going to be an X because we're calling the handler, which can handle it. And then if it cannot handle it, well, for now we can just keep it suspended like this, which has some problems. And then for that value case, we just keep it in the value case. And to just rapidly go through this, we match in the flatMap. We check to see if it can handle the embed. We're calling a random handler. It's a random node in here. So the random handler can handle the random node. Therefore, we're going to, yay, match on this, call random handler with next int, returning an int. Then call the continuation, which will get us back a console node. We recurse. We cannot handle the console node. So we're just basically going to return that suspended effect. Yay. Okay, and then we're basically going to return that final embed console print line. And then later on, we can do it again with console handler, which will actually match on the print line and actually do the print lining. And there's some more details, which I will click through very quickly so we can see. Obviously, just let that hit you. And then we're going to do live coding. So I'm bad at time management, but I hope that was interesting and got you started. Maybe I'll have to continue along some other time in some other format. But I will end there just to not torture everyone, because that was like an hour and 15 minutes of rapid fire rambling. I hope you got something out of that. That was fun. Thank you. Thank you, Magnus.
Yay, thank you very much. Actual live coding. You're fast at typing also.
I know.
Really nice presentation. You could probably sell this presentation to someone. You know, the actual code behind the presentation. People asking in the chat, like, what is the presentation tool you're using? Tool for the presentation.
Oh yeah, I wrote it in Scala. Use Scala. I wrote it in Scala JS, so Scala compiles down the JavaScript. So I made an animation library called Animus, and I'm using this great framework called Laminar, which is written for Scala JS, which is this functional reactive programming library that's way better than React. And yeah, so it's just all a custom stack, and it's super fun, you know.
Is it open source or is it your proprietary?
Not yet, but I could make it open source for $1 million.
No,
I could make it open source. I could make it open source eventually. I probably will. It's a bit of a. It's just like I keep cloning the previous presentation and adding to it, so it's a bit of a cluster. But I could do that. If people are interested, let me know. And if enough people yell at me, I'll put it out there, and we'll make a, we'll make an open source project. Then years down the line, we'll change the license thing. We'll do the Redis thing, and then we'll all get rich. And then there'll be a fork, and Apache will do it. Yeah, I know how open source works.
Yeah. First you have it open, and then you get money into it. Anyway, what are the main benefits of Kio compared to Zio?
That's a great question. Well, the biggest one would be speed, and that was actually the number one. I think you should definitely talk to Flavio sometime. Who is great, and he can answer these questions better than me. I think he's in the Discord, so I will give a bad answer and then let him correct. But I think one of the things is that it's super fast. By breaking, like that property of having this be modular allows the core of the language to be really simple and really small, actually, really understandable. I'll also share some gists where there's like the full toy implementation of Kio, which I think you might be able to jump the gap from where I ended the talk to that. Ask me any questions. But because it allows the core to be so small, because it doesn't have to deal with these thousands of different effect types, it really works well with the JVM and optimization there. So, and a ton of other fancy techniques that I don't understand yet that he's using, but super fast. It also has this ability to do things like that sequences effect for non-determinism, which is very powerful and cool. And you can't really do that like in Zio necessarily, or other things you need to use like monad transformers or some other data type that breaks you out of your for comprehension. You got to start wrapping things. So it's super composable. It's still new, and use it, try it out. It's fun. There's definitely lots of opportunities to like learn and contribute. Contributing to an early stage project's a great way to learn. I've learned a lot just by mucking around with it. So yeah, I defer to Flavio for the rest of the considerations.
Okay. Thank you very much.
Invisible. Thank you so much, and sorry for taking so much time. That was a blast. And
it was very interesting. Thank you very much. And to everyone that joins now live, jump into the Discord server to ask more questions. To Kit, Flavio, hopefully is there, and to Eduardo. And with that, to everyone that watched the live stream tonight, thank you very much, and either good evening or good morning or good afternoon, depending on where you are. And see you next time in May. Goodbye, everyone. Thanks.